at this equation of exponential growth. Let's read the learning goals. Don't highlight what I'm highlighting, right? It doesn't, that makes no sense. Just highlight if you need to highlight something. All right. I always found that the word model, when it came, a mathematical model, just was bonkers. I once had to create a mathematical model of a hip implant in university, and I still don't know what we did. A mathematical model for exponential growth is a bit easier to understand, but basically people who are true mathematicians or like whatever, really smart people, they will create an equation that models something. So for exponential growth, we can have an equation for the human population on Earth, and we can put dates in there to figure out approximately how many people will there be in 100 years, or how many people were there 500 years ago. If we create a really good equation, it will give us the right numbers. So that's what model means. Now we're going to talk about something called doubling time. And that's basically how long it takes for a population to double. So when we were looking at the video of cells of mitosis, the question is, how long did it take for one cell to become two? Then we're looking at a term called initial value. I think that's pretty clear. How many do we have to start with? And then the last thing is we're going to have to convert different times. So you know how to do this, but just a reminder. Good morning. Thank you. Just a reminder that if you have two times and one is in years and one is in seconds, we're going to have to convert it so that they have the same time. Exponential growth is used to model the growth of plant and animal populations, especially bacterial or single cell organism populations, right? So when we say single cell populations, we're talking about bacteria, we're talking about viruses, right? Because we can see one is splitting into two, into three. When we're talking about plant and animal population, that's like the curve that we talked about, the human population on Earth. However, it can also be used to model financial situation and economics, okay? As it relates to compound interest, mortgages, and inflation, okay? So let's look at this equation. If we're looking at population growth as an exponential function, okay, a convenient way to represent population growth is in terms of doubling time. Okay, and this is a very simple method, but it works. Doubling time is the time it requires for a population to double its value. Okay, since we're doing doubling time, we use a base 2 for the equation. Has anyone heard the term, what do we say, halftime? Because on Monday, we're talking about exponential decay. Yeah, half-life. In terms of like, if you've heard people talking about radioactive material, we talk about half-life, how long until half of that radioactive material has disintegrated, right? So that's exponential decay, where exponential growth, we're talking doubling time. So we really are wondering how long will it take a population to double? And then we can compare, we use that information to compare different populations. So let's look at this equation and let's understand what each of these variables represent. So the A at T, this is A stands for amount as a function of time, right? This is not A times T. This is the amount as a function of time. Another way we could think of it is the independent variable versus dependent, or input output. Looking at this equation, which one is the independent variable or the input? Time. How do I know? Well, it's in the brackets, right? The input is time because it's in the brackets. And then the dependent is going to be the amount or the output. Okay, this A naught, when you have a subscript of 0, that represents the initial. So this is the initial amount. And in terms of population, we would say it's the initial population. The T is the time that has elapsed. How much time has passed? So I'll write elapsed time. If elapsed doesn't make sense, it's really how much time has passed. Where the D represents the doubling time. And the D for a given situation is a constant. How long does it take for hair cells to double? Well, that's going to be the exact same each time. But what is going to be different is the input, the elapsed time. So we might say in 3 days, how many hairs will we have? Or in 5 seconds, how many hair cells will grow? Okay, let's look at an example. Now, FYI, on a test, I will give you this equation or this formula. Example 1. Go ahead and read it to yourself. Okay, underline or highlight the information that is given. Are we good? Can you move it back? There you go. You got it. You got it. A little more.
Wait, I didn't know which way it's supposed to go.
No worries. Yeah, because this is also turning.
Oh, okay.
All good. I'll go like this so it doesn't. Now, I like to do different colors for like what I need to do. And what's given, right? So for me, yellow is what's given. Okay. So remember grass or grasp? Let's use that. Right? You don't have to write these words, but follow that structure. And I know those of you who took physics and kinematics, you really felt how helpful it is to write these things down. All right. So to start off, let's see what information we're given. We're being told something happens every 3 hours. Well, it's a population that doubles. It doubles every 3 hours. So what do you think, which variable is every 3 hours represent? Good. So we're going to say D, i.e. doubling time, is 3 hours. Then we're told if there are 100 bacteria in the colony to begin with, what does that represent? Initial. Good. A naught. In physics, do they say naught? For if you have something like with the 0 at the bottom? No? Not really, eh? Okay. I don't know where I got that from. Some kind of course. You might hear me say A naught, and that represents the initial amount. So the initial population is 100 bacteria. What's required? Well, for A, we just need the equation. And for B, we need to determine the number of bacteria that would be present after 1 full day. So what am I solving for in the second one? Which variable am I solving for? Okay, talk to the people next to you. Determine the number of bacteria. So what are we solving for? Yeah. So folks, we are solving for the amount at a given time. What is the given time, the time that has elapsed? Why did you say 24 hours and not 1 full day? Because they're doubling in hours. We need the same unit. Okay. So in this case, T is 24 hours. And so how do I write it? I write it like this, A at 24. Because I'm saying the input is 24 hours. Okay, so let's start by just writing the equation. So the equation looks like this, the general equation where we don't know how much time has elapsed. Okay, but I do know that initially this colony starts with 100 bacteria. We're modeling it using doubling time. So the base of my exponential function is a 2. And then I have T over D. So T is going to be the input. That's the variable that's going to change. This is how my model works. I can put different times in there. Oh, no, not 100. And the D, it doubles every 3 hours, right? So this is a model. This allows you to say, hey, in 100 years, how many bacteria are you going to have? Hey, in 2 minutes, how many bacteria are you going to have, right? You can use this model. Now, in part B, we're being asked to use the model for a specific time. Okay, so in this case, T equals 24 hours. And so I want to find out what is A at 24, or A, the amount at 24 hours. So we write out the equation, and we're writing 2 to the power of 24 over 3. Now, before you punch this into your calculator, don't even. Luca, don't. You can do this in your head. What I want, the understanding part, the conceptual part, is if I simplify this, 24 over 3, what is it? What does that tell me? That 8 is telling me something. It's an important piece. What does it mean? Anyone else? Okay, watch this. If I have 100 times 2 versus 100 times 2 to the 2 versus 100 times 2 to the 3, etc., what does the 8 tell me? Yeah, Catherine?
How many times it's doubling?
Yes. It's telling me how many times it's doubling. It's like this. I start with 100, then I double, then I double, then I double. I doubled 8 times, right? Now, often when we do this work, the exponent doesn't end up being a whole number. We might get 8.3, but it's still really useful to understand, oh, that's what's happening. It's doubling 8.3 times. Okay, so can we do this in our head? Yeah. What's 2 to the power of 8? Don't say it out loud. Get your 8 fingers and go 2 times 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 times 2 times 2 times 2 times 2 times 2, 256. So this really is 100 times 256, which is 25,600, right? We're adding 2 zeros. Yeah. Of course, use your calculator. Yeah, we might have to use scientific notation. Absolutely. So what does 25,600 mean? Go back. I want you to write a sentence. Okay, read the question. Don't tell me. Don't ask the person next to you. Read the question and write a final statement. Therefore. Here's another question, folks. In that one day, how many new bacteria were there? Okay, talk to the people you're sitting next to. How many new bacteria in that one day? Is it 25,600? No, it's 25,000. Okay, good. Good. We're understanding what we're doing here. Excellent. Okay, let's do another question. Another human population question. Okay, same as before. Now, if you don't have a highlighter, I'm just going to show you how I do this. When I find information that is useful, I underline it, right? And then when I'm making a note of what I need to find, I'll circle it. That's how I'll distinguish. Now, don't underline what I underlined. Okay. There's a trick in this question. Okay, we're going to do one question at a time. Let's start off by writing down what we are given. I'm going to say that I'm given T1, right? Just so I know when time starts. Time starts in August 2018. Oh, actually, I won't call it T1. Sorry, I'm going to call it, what do you think is more appropriate? Because A naught is 7.6, right? So I'm going to say T naught or T0, right? So time starts at this time. If I have 7.6 billion, how do I write that in scientific notation? 7.6, 10 to the power of what? What's million? Okay, so what's billion? Good. Okay, then there's this growth rate situation, folks. I don't like it. I really don't like it. Do I need to use it? I don't. Okay? I want you to try to understand why I don't need to use it. Go back to the question. Why is it that this 1.09 is actually the question trying to trick me? It is not necessary to say that. Okay, go into your question. Why is that so? Who has a sense of why?
Because
Yeah,
we already have a doubling time.
that's it. So they're saying, sure, this is nice to know that the population is growing at 1.09%. The reason why we don't need to use it in our calculations is because of this pink stuff, which represents a doubling time of 58 years. So this percentage is information, but it's a bit of a decoy, right? We don't actually need to use it because we're told it's already been interpreted for us. What it said is if we grow at this percentage, every 58 years, our population will double. So that's the important piece, is the doubling time, right? So I'm not writing down 1.09 as a given. I'm writing down that the doubling time is 58 years. Okay, what is required? Oh, I guess there's another given. Yeah. Let's see. Okay. The other piece that's given in A is time. Let's just write it like this. Let's figure out what is the time elapsed. So I'm going to ignore the fact that they said August, because in 2025, I don't know which month we're talking about, right? But I need to figure out how much time has elapsed, how much time has passed. How do I do that? Talk to the people next to you. Is that right? Do we agree? Just subtract the time? Okay, good. So I've got 7 years that's elapsed. Are we good? Okay, and so what I'm required to find is new humans, which is not A at 7 years, right? Because I need to find the new humans. Let's start off by finding out how many we will have at that time. So we're going to find out A. Actually, not true. Is it? Yeah, we're good. So A at 7 years, the amount after 7 years. Our initial population is 7.6 billion. Folks, we're just going to write 7.6, and we're going to know that we're working in billions. Times 2 to the power of time elapsed over doubling time. So the time elapsed is 7 over 58 years. Will the population double in the 7 years? No, because we see it's 7 over 58. It's like a slice of a doubling. Okay, this is when I want you to take your calculators out, and let's learn how to use that calculator. Instead of 7.6 times 10 to the power of 9? Because this whole question is in billions. So whatever answer I get, if I get 2, I'm like, oh, that's 2 billion. I just don't want to write 7.6 times 10. You could have, right? That's not wrong. All right. So folks, you need to find your special button, which may look like this. on your calculator, or some calculators don't have that button, but instead they have a hat, which represents exponents. Does anyone, who knows how to use this button? Okay, if you don't, let's just practice. You would go to special button 8 would have to equal 256. Right? Just in case you're like, yeah, I'm not sure how to use this button, make sure you can at least do that problem. 2 to the power of 8 is 256. Okay? If you do know, then let's use this. Make sure that you're writing 7 over 58 either as a fraction or in brackets.
Wait, sorry, what do you mean either as a fraction?
Like if you're using the fraction button, okay. Yeah. Just so you're not saying 2 to the power of 7 all divided by 58 if you don't use the buttons properly. Okay, and we are looking, just because I've done this before, at approximately 8.3 billion. If you did not get that answer, ask me, ask someone. Let's make sure. It's really important that you know how to use your calculator for this question. Yeah. Well, is it the same as approximately 8.3, right? And let's not forget, Miss Sly really is picky about those equal signs, those approximate equal signs. I will tell you how many decimals to use because in math, we don't teach you significant digits, right? Some of you know significant digits, go for it. But I should be telling you how much. Yes.
If we know significant digits, should we go that way? Or?
No, you can always, because I actually forget the rules of significant digits. So yeah, I should always be telling you how many digits. Okay, am I done? Is that the answer? Go back to the question. Is this the answer? It is definitely not the answer, right? What am I supposed to find? New humans. All right, so let's figure that out. And we're going to, because we're using an approximated number, we need to still use the approximated equal sign, right? This represents, hey, the numbers I'm using aren't exact. Okay, that's an important distinction to make. So it's 0.7 billion, or how many million? 700 million, that's right. Okay, so that's how many new humans we have. We good? Questions? All right, let's move on to the next part. Now we're asked to go backwards, folks. We're asked to find out what was the population in the year 1900. Okay, don't worry about the nota bene for now. We'll get back there. Okay, now we're still using the same model. So our model but here's the question. Let's think logically. If I'm going to 1900, should my number be increasing or decreasing? Significantly, right? I'm going down the exponential curve. Now, how do I make that happen if I have to do 2 to the power of something? Ooh, because if I have 2 to a negative exponent, let's just say whatever, -5, what does it become? 1 over 2 to the 5. And now I'm dividing. So I'm making the number smaller. Beautiful. So I'm like recognizing, oh, I need to have a negative exponent. Interesting. All right. So how do I figure out my time? Well, I'm going to need a negative. So what I'm doing is I'm saying, all right, let's do the time that we're asked for minus the initial time. Just like we did in the first question. And I get that the time elapsed is negative 118. And in this case, this is like a vector. You know how like if you have a negative uh, displacement, it means you moved backwards in physics. So this negative is giving us a direction of time. It's saying, hey, we're going 118 years back. Does that make sense? So the negative tells us 118 years back. Okay, so we want to find out what is A at negative 118. Before you punch it into your calculator, approximately how many times do you think it's going to go in half? Look at the exponent. How many times does 58 go into 118? Approximately? About twice, right? So we're going to half the population twice. So it's going to be like 3.8 and then like 1.7. So we're looking at something around 2 billion is my very quick estimation. All right, pop this into your calculator. I want everyone to be punching this in. Round it to 1 decimal. Are we agreeing? Would you be able to figure out by how many new humans were born since the year 1900? Yeah. Now, here's the question. The actual number. Now, if we go up to the note, it says nota bene NB. It was actually 1.65 billion. So explain any discrepancy in your calculations. So why is it? So it was actually 1.65. So what could have caused a difference? Yeah. No, it's not rounding. Ryan? Total human factors like war, disease. Yeah.
Like just random human death? Just like kind of like anything out of what the expected is based on the.
That's right. Right. This model is generalized, right? It's like a general model. Hey, we think that you're going to have this percentage of death and birth each year. Well, but then you have a war, so you have more deaths, but then you have the baby boom, more births, but then you have COVID and polio and the plague and smallpox and all these diseases, right? So because of all these other small human factors, this model has some shortcomings. It's a good approximation, but it has shortcomings. Yeah.
So we have just taken out 7.6 billion and subtracted 1.6.
You're good? Okay. Yeah, I think you were thinking about another question. Okay. Here's a question. How much will the Earth's population grow in one day? So what they're saying is, what is the time elapsed here? 1 day or 24 hours? Eden, what are you thinking? Because you asked this question before. You alluded to, like, you don't even realize, but your question is important now, right? So, like, we're being asked in one day, how much is time? How many humans are born? So what do I put in my equation? Do I put in 1? I cannot put 1 because what is this equation based on? Years. It's based on years. The doubling time is 58 years. So, 2 options. 1, change the doubling time into days or hours, or 2, change the time elapsed into days or hours, or sorry, into years. I'm going to do that because I want to keep the model, I want to keep the equation that I have. So we're going to do this based on a year of 365 days, no leap year. So that means that the time elapsed is 1 over 365 years. Does that make sense? 1/365th of a year. Yes.
You didn't do it like the other way of taking like the
Yeah.
58 years into
Yeah.
days. Would you still get the same?
You would absolutely get the same answer because the T over D is a fraction. It's a comparison of 2 numbers. So you would need to get the same. All right, so let's write our model. We're saying, what is the amount after 1/365th? Right, that's the time elapsed. Isn't that ugly? Okay, well, we've got 7.6 times 2. Now we're going to have a messy exponent. 1/365th over a doubling time of 58. Yum. Yeah. We're going to do some math. Yeah. So we're going to say, okay, if I have 1/365th and it's divided by 58, do you know how to do this? If you're not sure, make 58 into a fraction. And what's the word? What am I going to do? I'm going to multiply by the reciprocal. So 1/365 times 1/58. So we're going to have a really small number. One 21,170th. I don't even know how to say that. So what we're punching in is we're saying 7.6 times 2 to the power of 1/21,170th. Am I looking for a huge number or a small number? Okay, good. That's CTB. That's critical thinking brain. Anticipating an answer. In anticipation, I know I'm going to be rounding. Or do I have to round? Okay, what I have in my notes is 7.600249. Is that where it stops? No, it keeps going. Yeah, okay, good. So I need this approximate equal sign. Now, why didn't I just round to 1 decimal place? Okay, I want everyone to think about this. Go back to the question, why didn't I round after 7.6? What is it, Luca?
That'd be the same population as before.
Right. We're looking for a really small number. So we got to get far into those decimals. Okay, so let's see. In one day, or let's go like this, amount in one day. We're going to go 7. Now, again, I'm using an approximated number, and I'm just communicating that by using the approximated equal sign. Right, so I'm subtracting what the current population is, after, like, from the initial population. So that's 0.000249 billion. Here, I'm going to use scientific notation.
Okay.
Because I don't want to write it like this. I want to write it in proper scientific notation.
And should we leave it in scientific notation?
Depending. Let's see what we end up with. Okay. So I'm going to be moving my decimal all the way here. Right? So if I move it, so let's see how many spaces I'm moving it. 1, 2, 3, 4. Okay, so that means I've got 2.49 times 10 to the power of 9 times 10 to the power of negative 4. Okay, because I just moved it in the negative direction. Yeah.
Can't you just move the decimal place of 9 spaces back? That's 7 points.
You could. Yeah, you could. Yeah. That might be simpler. So Ryan's like, why don't I just move it 9 spaces back? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And this becomes your number. I like that. That's better. Because I'm going to have times 10 to the 5. And essentially, we get 249,000 people born in one day. Oh, not born. Sorry, because we're not.
Is it not born?
No, because people also die in one day. So there's a growth
Oh.
of 250,000. That, yeah,
You have to keep the approximated
yeah.
signs on.
Okay, so we're changing gears. Now, I get that you might not want to do this homework today. That's fine. You might want to study for the quiz today and then do the homework over the weekend, right? Because I'm not going to give you homework tomorrow. So that's not a problem if you choose to do that. Okay, there will be extra help today.